Alrighty, here we go. So now we're on the long anticipated math bit of this. And here today we're gonna go into the basics of calculus. And this is gonna be real basics, you know, like the Reader's Digest would be more intense than what we're gonna do. But there's not gonna be that much. There's just gonna be limits, derivatives, and maybe a little bit of differential equations. And at each step, I'll go over a little bit about how they are relevant to quantum mechanics. And hopefully, it won't be too crazy. But, you know, trust me, it looks harder than it really is. Or at least, that's what it will be. Anyway, let's get to it. So, limits. There's not really that much to this, but how should I put this? Suppose that we have an equation y equal to x. So we have this function, looks a little bit like this, with x here, and y is the vertical axis. It will look a little bit like this. Oh, that does not look right. Like that. Now, let's suppose I have a question about the behavior of this function. And my question is, as x goes to, let's say, 4, what is y? And it's not going to be an equal sign. Y is equal to what? Now, in this case, this is fairly simple. You're just going to go look for x equals 4, and you're going to put up, and it's going to be at, y equals 4. It's not that complicated right here. Trust me, limits are not that dense, but they can be kind of helpful. Because, this example looks kind of contrived, kind of it's goofy almost. But let's say that this isn't our function. Let's say it's something a wee bit more exotic, like e to the x. Now, it will not look like this. Instead, it will look, I don't know why we need the negative part in there. If this is x graph, or e to the x function, will look a little bit like that. And let's say we're not interested at what happens when x is equal to 4. Let's say we're interested to see what happens when x is equal to negative 1 million. No, not 1 million. Negative infinity. Obviously this might sound kind of like a weird question. Like, what do you mean when x goes negative infinity? What I mean by that is that when x goes this direction forever and ever and ever, what y value does this approach to? Does it approach y equals, hang on, that's not right. Does it approach y equals 1? Does it approach y equals 3? Or y equals 0? Or negative value? Or where does it go? Where is our equation heading? And sometimes this can be very helpful, because as you can see here, if you know anything about exponential equations, you will know that when x becomes like a very, very, very negative number, e to the x will actually approach 0. It won't actually reach at 0, like if we set 0 equal to e x, e to the x, there is no solution for x that will ever equal 0, because you would have to multiply e to an exponent and get 0, which is impossible. But e can approach 0, in this case. And if that might sound a little bit useless, and in a way it kind of is, mostly has a use in math. But remember, this is about quantum mechanics. So let's consider a different thing. Remember, in quantum mechanics, we have to deal with wave functions in terms of things like x, or t, or whatever. And so a wave function will look wavy, or it might look something like this, or it might look like this, or it might take any manner of forms. But let's imagine something like a free particle. Say like I have an electron gun that shoots an electron, say at a detection screen. Now we want a wave function to model this particle. And obviously it helps if you remember that wave functions are helpful for things like they're somewhat connected to the probability of finding the particle. So let's say that we have, I don't know, we'll say that this is the x-axis. For now, we're going to ignore time, pretend like time doesn't exist for the moment. We're only going to worry about one dimension of x. And, we're just going to make this vertical axis equal to psi, which is the amplitude of our wave function. Remember that this is loosely equal to probability. Well, let's think of, a wave function like, I don't know, x squared. Well, it would look a little bit like this. And this is not a very good wave function because, as x approaches some value over here, it's going to get to infinity, which is not what we want, because that would mean that like the further away you go at this direction, probability goes to infinity, which doesn't make much sense. So what we want, for things like free particles, we want it such that, when x goes to positive or negative infinity, we want psi to go to 0, at least most of the time. And that means that the wave function has to look a little bit like this. It doesn't have to. For example, it could look a little bit like this. All that really matters is what happens at these end points, that they have to go to 0, because that means that we won't find the particle far away. But I don't want to spend too much time on limits because they're not that dense and they're very simple. But hopefully this is enough, because we are now going to go on to derivatives, which are much more important. All right, derivatives. So just like last time, I'm going to start with like an arbitrary math equation, and then we'll work it into physics. Although I might dabble more in it in another video on quantum aspect. Anyway, suppose that we have a different equation. Say y equals to x. And let's say that I wanted you to tell me about the slope of this graph. Or maybe, I don't know, the gradient, or whatever you want to call it. In this case, we're going to call it the word derivative. But these are all synonymous terms. Point is, we want to know the slope of this graph. How fast does it go up? And in this case, this equation is going to look a little bit like, you probably know it already, but it's going to look a little bit like this. It will have XY grid. It's going to look a little bit like that. And if I want you to find the slope, if you remember anything from like kindergarten, or maybe not kindergarten, but like long ago, you might take, say, some term, the x distance, we'll call it delta x for now, and you would take the y distance, which you call delta y, and what you do is you would say that the slope is equal to delta y divided by delta x. And from functions like this, which we call linear, these are not that bad. This would be the end of it. But what if it's not y equal to x? There are many things in nature and engineering and much more that do not look linear like that. So let's say that this is not y is equal to x, but x squared. And you know what? Just to make it easier to visualize, I'm going to add, something like this: x, y, and we'll have them intersect like that. Now in this case, the function will look like this. And let's say I want you to help me find the slope. Well, you might start by doing what you did earlier with like a delta y and like a delta x. But here's the issue, is that it's not constant, because here it might look like that. But what if we want to find it on a larger area? We can have delta x like that, delta y would be something huge, and we would get a much bigger slope than before. Or, we could say take a e to be a little slope of x and an e to be a little slope of y, and we'd arrive at a tiny slope. What we need is something that can give us a slope at every point. Because, for example, at this point, the slope is equal to 0, and at this slope point, slope might be equal to like 2, and here the slope might be equal to like 10, and here the slope is going to be equal to like negative 10 or something, and it varies. And the answer is the derivative. And I'm going to erase this for the moment. And we are going to introduce some notation which will become very relevant in the future. So you might recall from earlier that we had the equation delta y divided by delta x as the slope, But we are actually going to do a new type of equation. I hate yellow. We're not doing yellow. New notation, which we shall call dy divided by, hang on, dx. And this d, the little d, is the same thing as the big triangle. However, in this case, it refers to an e to be a little change. In fact, an infinitesimal change. And this thing here, dy over dx, is what we call the derivative. It's singular, Yeah, that's perfect. We'll see. This whole thing is the derivative. And what does it do? Well, what it does is it turns one equation into another equation. So, I was going to go through the process of finding the derivative, but it might take a little while. Screw it. I can do it. So, how do we write this out? Well, what we do is we take, I'm going to color code it. dy over dx of x squared. And maybe in like another time I'll I'll go through how to do this, but all you need to know is that this function would turn into 2x, and that is the slope. You plug in some value for x and it gives you the slope at that point. And why is this relevant? Well, let's say that this is not y equals to 2x squared. Let's say that you are doing some rocket science and you have the equation for a rocket's position over time. So h of t is equal to, let's say, 30t cubed, where h is equal to the height of the rocket. And, it'll look something similar to this. So t, we measure in seconds, h is the height, and it's going to look a little bit like this. And let's say that the NASA or whoever it is, they tell you that the engines will run out of fuel at around, let's go with 10 seconds, just for example. And they want to know the velocity at the rocket at that point. Well, if you've ever studied a little bit of physics before in like high school, you might know that velocity is equal to x over t, where t is time and x is seconds. In this case, we will use a different way of doing this, where v of t is equal to dh, because we're using h instead of x, over dt. And I'm not going to do the operation this time either, but essentially, if we take the derivative of this equation, it will give us 90t squared. And so when we plug in t equals to 10, then the velocity is equal to 100 times 90, which is about 9,000. Whatever unit it was. I didn't actually specify unit, and I will make more videos on calculus one of these moments. But right now we're worried about quantum mechanics. And you might be telling me, oh, well, how is this relevant to quantum mechanics? Well, I'll explore it in another video next time, because I don't want to be too much at once. And everything. But the thing is, how should I put this? Technically, derivatives go into differential equations. So I'm just going to put it here too. Diff equations. This is sloppy handwriting. And you kind of saw an example there of differential equations. Hang on, let me move this out of the way. Hang on, nope, that's what I want. There we go. Yeah, that should do. Anyway. So differential equations, kind of just saw an example of it, but basically v is equal to dx over dt, and this is a little bit of notation here as well, but acceleration is equal to d squared x over dt squared. And this here, just like this notation here, just means you take the derivative twice. So take derivative once, turn it to an equation for velocity, then take derivative again, it turns it into an equation for acceleration. And it's called differential equations because acceleration depends on this derivative, and velocity depends on this derivative as well. And I won't go too much into depth just yet, but the Schrodinger equation, I better write this down. This will come up next time. But the road. I better make sure I'm spelling this. Okay, I was spelling this correctly. Schrodinger. He was a German. That's why there's dots on his head. Equation. Anyway, Schrodinger equation. Because of many forms, we'll focus on the time-independent Schrodinger equation, which will look a bit like this. I'll color code it because I like color coding. D squared psi over dx squared. Oh wait, we have to put the constants here. Negative h bar squared over 2m plus v of x times psi is equal to the energy of psi. And if I showed this, how should I put this? I mean, already you can kind of make out what this is supposed to be here. This is how the height of the Schrodinger, the wave function changes over space. So if you can imagine it as like if you have a set of mountains, it's how high the mountains, how steep the mountains are essentially. In this case, it's how steep the wave functions are. So when the second derivative, when it's close to zero, that means you're living on like a flat wave function where there's basically no probability. And when the second derivative is very high, then that's a steep wave function. This bit is what we call a potential. And it's not very we won't go into too many examples, but it's basically something that restricts the wave function in some manner. And this basically tells us together, it gives us the energy values, or what sort of energy we have. And we'll go more in detail about it later, next time. I'll also give other examples of how calculus works in physics. But, I don't know, maybe I've overstepped my bounds, because I might have gone too far. We're going to focus more on differentiation a little bit, so you can get used to the notation. Like imagine we're working with a wave function, like say, I don't know, some value of x cubed is equal to, let's call it phi of x. Well, the derivative would be d phi of x with respect to x. And in this case, in case you're wondering, the derivative would be 3x squared. And if we could take the derivative again, then this would be, d squared of phi divided by d squared of phi divided by dx squared. I'm probably saying this wrong. These are not squares. These is second derivative. Take derivative again, and it will turn into 6x. And you can keep on going, turn it into like d3 phi and dx3, which will eventually get you to 6. In my next video, I will go over some more physics examples and the Schrodinger equation a little bit more. But it's very relevant that you know some of this notation when we get into it again. Anyway, I hope this was informative enough. I really watered down some of this stuff, which I'm going to make another one. Anyway, see you next time.